So I'm going to be talking about the application of functionalized non-woven veils to address the challenges of EMI shielding, fire performance or thermal runaway in composite batteries. Next slide, please. So we're going to look at a brief introduction to TFP, the challenges in composite EV battery boxes, TFP's materials and their historic use in composites, and then drilling down into how functionalized technical non-wovens can be applied to address these challenges of EMI and FST or fire and thermal insulation performance, and then a brief summary at the end. Next slide, please. So a little bit about TFP. Who are we? We're the leading manufacturer of technical non-wovens and electrochemical materials. Been around for about 35 years. We supply into a very diverse range of markets, from aerospace, fuel cells, through to water electrolyzer markets. Extensive converting capability, and we have 4 manufacturing and converting sites. We're headquartered in the northwest of the UK, the Lake District. We have a manufacturing plant in Crewe in the Midlands, a recent acquisition of TFP Hydrogen Products down in Cornwall, and then TFP Inc. based in upstate New York. And we're part of the James Cropper PLC group, which is a heritage paper company that's been around for 175 years, has 600 employees, is listed on the London Stock Exchange. Next slide, please. So we're all here to talk about composite battery boxes, and there's some fantastic statistics. And one that really caught my eye from one of the market surveys was in 2019, 2.5% of cars sold were EVs. That's forecast by 2029 to be 25%. So really, really significant growth, depending on which market survey you look at, running at 20 to 30% CAGR. And we know that composites offer several advantages for battery enclosures, and it's really that the classical balance with composites of performance versus weight, or properties versus weight. However, through their application, they do also present some challenges in terms of EMI shielding, electromagnetic interference shielding, and fire protection. Next slide, please. So what does TFP make? Well, we make non-woven materials based on a very wide range of fibers, from carbon, glass, polyester, thermoplastics, basalt, metal-coated fibers. So pretty much any fiber we can apply through a wet lathe process to make a highly porous fibrous sheet with tunable properties. And it's really that tunable properties I want to focus in on. So they can fulfill a range of applications in composites, often simultaneously. What people tend to focus on and think about with lightweight non-wovens is surface finish. The application of a lightweight glass or polyester veil to give a resin-rich surface layer. They also find widespread application as fabrication aids, such as adhesive carriers, resin flow media, in fracture toughness. But what really excites me is surface functionality. The ability to be able to tune the product through selection of the fiber and the way the fiber is incorporated into the veil, and potentially other additives to give a higher level of functionality. So as well as the surface finish, to be able to give a simple drop-in lightweight veil that offers EMI shielding, electrical conductivity, abrasion resistance, corrosion resistance, and fire protection. And it's really the EMI shielding and fire protection that we're interested in today. Next slide, please. So if we look at EMI shielding for battery enclosures through application of a functionalized non-woven veil, next slide, please. So a non-woven veil can offer a lightweight, effective, and easy to incorporate EMI shielding solution. These solutions have been around for a long time and have found very widespread application in the composite market in various end market segments. So if we look at the graph on the left on the x-axis, sorry, can we just go back one? On the x-axis, we have frequency in gigahertz. On the y-axis, we have shielding effectiveness in dB and decibels. And this is looking at a copper and nickel coated carbon at 1 to 8.5 gigahertz. And we're looking at different aerial weights. So if you look at the bottom line, you can see with a 4 gram of very lightweight metal coated carbon, we're achieving about 30 to 40 dB of shielding effectiveness. As we move up through the aerial weight through 10 to 17 grams, we're up at about 60 dB effective shielding, and then up to 34 grams, you can see we're into 70 up to 90 dB of effective shielding. So through selection of the particular fiber and the aerial weight of the veil, we can achieve very, very high levels of tunable shielding application, shielding performance. And at a very, very lightweight in terms of, in comparison to metal and in terms of application to the overall composite part. Next slide, please. So in this table, we're really looking at three things here. The most important part is we're comparing the shielding effectiveness of the veil on its own to veil incorporated into a composite part. We're looking at a comparison of carbon, nickel-coated carbon. Sorry, can we just go back one? Thank you. We're looking at the comparison of carbon, nickel-coated carbon, and copper and nickel-coated carbon. We're looking at different aerial weights. So you can see by increasing aerial weight, we get an increase in shielding effectiveness, going from 10 to 17, 11 to 17. You can see moving down the series from carbon, nickel-coated carbon to copper and nickel-coated carbon, we see an increase in shielding effectiveness. But most importantly, if you look at the two columns on the right-hand side, you can see there's very, very little drop-off in terms of EMI shielding effectiveness, moving from the veil as is, so assessing the performance of the veil standalone, to the veil incorporated into the composite part. Next slide, please. So in terms of EMI shielding, what are the key benefits? Lightweight and thin, excellent shielding relative to the weight, good flex fatigue performance and conformability due to the lightweight nature of the veil. Or we can tune the shielding effectiveness by the aerial weight and the choice of type of fiber. And these veils are designed to be easily incorporated via a typical range of manufacturing techniques. And from the projects we're involved in, a whole range of different manufacturing techniques, from pre-preg, filament winding, compression RTM are used, and these veils are very applicable to those techniques. Next slide, please. So if we move on to the FST requirements, the thermal requirements for battery enclosures. Next slide, please. So the Technofire range of lightweight intumescent fire protection materials have found widespread application in composites. So these are lightweight, non-woven veils that incorporate graphite that, under the action of heat at 190 degrees centigrade, or we do have materials that activate at 220, and we are working on materials that activate at 250 and 280. They expand or intumesce in the Z direction to form a stable, insulating carboniferous char that protects the backing laminate from heat and oxygen getting through to it, and any potential liberated fuel gases from escaping. And these products have been established in composites for well over 20 years. Next slide, please. So this is a fairly wordy slide that I'm going to kind of summarize. I think we're all aware that probably the most demanding thermal or fire battery standard up to date has been the Chinese bonfire test, the GB31467, which is a pretty demanding test for composites to successfully pass. The composite enclosures are exposed to surface temperatures of greater than 600 degrees centigrade for 2 minutes, with peaks hitting 800 degrees. Those standards have now been updated. The GBT 38031 is really the most applicable one to passenger cars. And that now incorporates a 5-minute egress alarm, and the structure must withstand higher temperatures, over 1,000 degrees at the surface of the enclosure for longer periods. Next slide, please. I'm just going to touch fairly briefly on an ongoing project we have with Ford Engineering in Germany, and I'm absolutely delighted and need to say thank you to Ford for agreeing to allow us to present some of this data. And this is a fairly in-depth evaluation of flame testing of intumescent veils in composites. And the initial phase of this project involved 36 experiments with 3 different intumescent veils. incorporated into composite structures. They were tested at 800, 600, and 400 degrees centigrade with direct gas flame impingement, exposure on the coupon. There's a degree of ablatement as well as the actual thermal temperature that the parts are seeing. Exposure times of 5 and 15 minutes. And the maximum temperature that was seen on the 800 degrees C test was really about 300 degrees centigrade on the back face. So we're seeing roughly a 500 degrees C insulation value between the flame side and the back side. Next slide, please. So this somewhat complicated graph, I can simplify fairly quickly. This is involving T66301, which is a very lightweight intumescent veil. So this is a 70 gram per square meter veil at 0.37 millimeters thickness. On the x-axis, we have time. On the y-axis, we have temperature. And this is one of the 800 degrees centigrade runs of experiments. You can see the top line, the surface of the panel is achieving 800 degrees. You can see some of the experiments are stopped at 5 minutes, some at 15 minutes, and some of the experiments allowed to run on to 20 minutes. And if you look at the lines towards the bottom of the graph, you can see that we're seeing temperatures really between 150 and 250 degrees centigrade on the back face of the laminate. We're seeing insulation values of 550 to 650 degrees centigrade for incorporation of the Technofire intumescent veils. Next slide, please.
You got 1 more minute, please, Neil.
Thank you. And these pictures just show the worst case damage really on the T66301 Technofire enabled composites. So the picture on the right shows the flame impingement side, where you can see some of the resin has been ablated off, it has been burnt off. But the picture on the left shows the back side of the actual laminate. You can see there's no distortion, no degradation, no damage, and just some discoloration over the surface. So you're seeing that the Technofire is effectively insulating the back of the laminate structure and preventing degradation. Next slide, please. So just to sum up, the move to production of composite batteries offers many advantages, but some challenges, EMI and thermal performance, or FST, being a key one. And the use of drop-in functionalized nonwovens provides some quite significant solutions. So ideal for use in composite design and manufacturing, very simple to incorporate lightweight functionalized veils. There doesn't have to be a change to manufacturing process, resin systems, or reinforcing. They can impart effective EMI shielding. Resin-rich surface finish can be an additional benefit, and the Technofire intumescent veils can help meet requirements in the fire test standards. And one thing I'm really interested in is we've started looking at some materials that we developed in the lab that incorporate both types of technology, and we have the potential to offer both EMI shielding and FST performance in a single functionalized veil. Next slide, please. So that's a very, very short, sharp summary. Very happy to take questions now. We're in the breakout rooms. Thank you.
Brilliant. That's really, really good. There's some excellent results on that one, Neil. There's really, really good work. So we've got a few questions in the chat. One from an anonymous attendee. Are the veils compatible with different resins and processes, i.e. pultrusion?
Yes, they are. We have ongoing commercial use of the veils with epoxies, with polyesters, vinyl esters, polyurethanes, prepregs. We have some specific veils that we've developed for use with phenolics, where the acid catalysts can be a bit of a challenge, but we've tuned the performance of the veils for those applications. We have ongoing commercial business in pultrusion, RTM, filament winding, vacuum infusion, and having the ability to tune the veils ourselves, both in R&D on a pilot line and in production. We can modify the veils to really optimize them for the specific application. But they are used either in development or commercially, really across all resin systems and all manufacturing techniques.
Great. One more question before we move on to the next presentation, which is from Daniel Jessup. Do you see these veils as a product that can be used in an injection molding process in any way?
There we do need to be careful with the pressures and the type of resin used. So we do have veils that have been used in SMC type processes. We need to be careful specifically around if there's a filled system around degradation of the veil, but in an unfilled resin, compression RTM, the products are being used in. So I believe with careful selection of the right veil, the answer to that is potentially yes.